Can you find this function hidden somewhere within this function? Well, the first thing I'd do is take the 6 out, so we'd square it, that becomes 36. Now I need that 36 to turn into a 3, so I can separate 36 into 12 times 3. Now we can see that function 3 times x plus 1 all squared. This is called manipulating the expression, and it's the first step of 3 for integration by recognition. Don't forget to download your template that's linked below so that you can put it in your resource book. Let's go. Differentiate, hence integrate. That's what the question's going to say, and that's how you know you're going to be using integration by recognition to solve your problem. Here is the key idea. If I differentiate a particular function, if I want to go backwards, all I need to do is integrate. Differentiating and integrating are opposites to each other, so it should be pretty easy to be able to go back and forth between two functions. This is the first line I always write whenever I'm completing a question, and then we'll be able to follow the 3-step method to get into the answer. So, what is the 3-step method? Here are the 3 words you need to remember: find, isolate, evaluate. So, the first thing you need to do is find the required integral. What's the question asking you to find? It's going to be hidden somewhere in your differentiated function. You just need to be able to find it by manipulating the equation. Then you're going to isolate. So, once you've found it, everything else that's there that's being multiplied or added, whatever it is, needs to move to the other side. And then lastly, you'll just evaluate. So whatever's on the other side, sometimes it'll need integrating, sometimes it'll need simplifying, whatever you need to do to it, just do that and then you'll get your answer. Now, the hardest step of these, I think, is one, which is to find the required integral, because you have to change the way the function looks to get to the integral that you want. There are lots of ways to being able to do this, but here are 3 examples. So in our first example, introduce missing factors, what you can see is that these two functions look different, but they're actually exactly the same. The only difference is that this has an introduced factor of 2, but I can't just randomly multiply by 2. I need to make sure that it's balanced out by also multiplying by the opposite, a half, because a half times 2 is 1. So really, it cancels each other out, and I haven't done anything to change the function. It just looks different. Same with the second one, factor constants outside. Say I have a 6 on the outside, but really I want it to be a 2. Well, you can break up the 6 into 3 times 2, and now I've got the function that I want, and I've got something else on the outside that I'll deal with a little bit later. Also, don't forget that you can separate terms. This is one of the key identities of antidifferentiation. If you've got multiple terms, you can separate them. In this specific case, don't forget to expand first, but this will help you get to one particular function if that's what you need within your expression. So here are some examples of how you can change a function. Once you've done that, parts 2 and 3 are generally quite straightforward to do. So let's do an example together, example 1, and then example 2 is for you to try later on and let me know how you go or if you need any help with it. So let's give it a go. Part A says differentiate x sine x. This is two functions being multiplied with each other, so we need to use the product rule. So I'll quickly write down my two functions, differentiate them separately, and then remember all you need to do is multiply across. So the derivative of x sine x is going to be equal to x times cos x, because I'm multiplying across, plus sine x. Now here's our key idea. If I differentiate x sine x, I get x cos x plus sine x. And if I want to go backwards, all I have to do is integrate it to get to my original function. So for part B, when it asks me to evaluate the integral of x cos x, the first thing I'm going to do is write that particular concept. That if I were to anti-differentiate the answer that I just got, I would get back to my original function. This step is really important and is going to set the scene for the rest of the steps. Okay, now we're going to have a look at what they're asking me for. We're going to anti-differentiate x cos x. That's this part over here. I've got a sign in the way, so I need to take that over to the other side, but before I can do that, I need to be able to isolate the x cos x. We're going to use one of the manipulation strategies, which is to separate the terms. So if I separate x cos x dx, remember that I can then write sine x as a separate integral. And now I can very easily see that the required integral x cos x dx is right there. So that's what they've asked me for, and I've been able to find it. That's step 1. Step 2 is to isolate. So that means everything else needs to go to the other side. So the integral of x cos x dx is equal to x sine x and then minus sine x dx. Finally, for step 3, all I need to do is evaluate anything that's left over. So x sine x, we can't really do much, but I can integrate sine x. Anti-differentiating sine x is going to give me negative cos x. Negative and negative makes a positive, so that'll be cos x. And then don't forget to write plus c as well when we integrate. So that means when I anti-differentiate x cos x, I'm going to get x sine x plus cos x plus c. You can see that I haven't really integrated anything. I did do this one, but I haven't integrated x cos x, and yet I got an answer because I have my original derivative. That's what integration by recognition is all about. So this is integration by recognition in a nutshell. Let me know if you have any questions about this topic or if you'd like me to cover any other topic as well. Good luck.